Hello, my name is Maximilian Rettinger. I'm a PhD student at the Technical University of Munich, and I will present you the paper titled Defuse the Training of Risky Tasks, Collaborative Training in XR. Many publications have demonstrated the exciting opportunities that XR offers to improve training and increase trainee safety. But a variety of them investigated single-user scenarios, so the users completed the training without an expert or instructor. However, it is not advisable to complete the training without an expert in critical or dangerous scenarios, such as ordnance disposal training. Probably most of you are familiar with the current situation in Ukraine, but do you know that, for example, a female English teacher is trained to become an explosive ordnance disposal expert within 18 days? That sounds absurd, but it is a reality in Ukraine in 2022. This is because various explosive ordnance, such as cluster bombs, landmines or grenades, are used during a military conflict. Cluster bombs are particularly hazardous for civilians since they contain submunitions with a high dot rate that spread impressively over a large area. Due to the submunition's small size and the large scattering areas, these explosives are difficult to detect by civilians and explosive ordnance disposal teams. Consequently, history has shown that by the war's end, about 40% of the killed and maimed civilians were children, while 50% of the civilians' casualties were attributable to cluster bombs. Therefore, there is a need for a large number of explosive ordnance disposal experts, while the civilian population also contributes to removing them. For this, the experts need complex knowledge because of the large number of different types of explosives ordnance worldwide. For example, these ordnances differ not only visually due to their shape or size, but also in terms of explosives used, their construction and their ignition mechanisms. Identifying the explosive device is essential for assessing the associated risks and diffusing or detonating it in a controlled way. Thus, interaction experience and complex knowledge from experts are required, so collaborative XR training could be suitable for this purpose. To investigate this, we chose the training procedure and content in such a way that no prior knowledge was required to avoid overwhelming the participants and to create comparable conditions. For this, the Soviet F-1 hand grenade was proved suitable as an example. Thereby, we designed the training content in cooperation with a training center for explosive ordnance disposal and a humanitarian foundation which focused on the functionality, the component designations, and the implications after detonation. The training procedure was divided into 10 steps. In steps 1 to 9, an instructor explained the relevant content, followed by an open training in which the participants were able to study the corresponding training material by themselves, while the instructor was still present to answer questions and clarify ambiguities. All this knowledge should allow the participants to identify this type of ordnance, assess its status, for example, secured, armed, or DAT, and evaluate the associated risk. By using this training content, we explored the suitability of virtual methods for training civilian explosive ordnance disposal experts by comparing these three collaborative methods: the conventional real training, the HMD-based virtual reality training, and the cave-based mixed reality training. In the real-world training, as tools, we used a 3D printed replica of the grenade and a 2D drawing on a paper sheet for assigning the components designations. The 3D printed replica is one of the most up-to-date tools, designed by the Advanced Ordnance Teaching Materials program. Its firing mechanism can interactively be tested by pulling the safety ring, whereby the firing pin is no longer fixed and is pressed against the primer by the force of a spring. The cross-sectional view and the different color-coded model components help to distinguish between the grenade's technical operation and inner composition. In the VR and MR training conditions, the component designations were next to the virtual grenade. The virtual environment of the other two conditions included a virtual touchscreen to control the respective steps and a table to place a grenade on it. As seen in the image, the grenade on the table could also be scaled in order to see certain components more clearly. This figure shows the VR training in which the instructor and the students were an HTC Vive Pro. The student holds the grenade by using the grab function of the controller. Both people were represented as avatars whose movements were stabilized by inverse kinematics. Since it was a multi-user application, both people could perceive each other in real time. A four-sided cave was used for the mixed reality training, which is why the people wore shutter glasses. Since the experiment took place in a single-view cave, the experience was only correctly rendered from the student's perspective, which means that the co-located instructor couldn't perceive the virtual environment correctly, based on his position and view. Since this study did not refer to the instructor's performance, the student was not influenced by this limitation. We designed a between-subject study to compare the real training, virtual reality training, and mixed reality training approaches in a controlled lab experiment to assess differences in training success. As dependent variables, we considered the training duration, the user experience, the workload, the subjective interest, subjective training success, and learning success by an online test. For the experiment, we recruited 75 participants, which were equally distributed to the three conditions regarding age, gender, and level of education. With a study briefing, questionnaire, and VR tasks, the study took about 10 minutes per participant. There was a significant difference in the training time between the conditions, indicating that participants in the VR and MR training spent significantly more time. After completing the training, participants rated the user experience in a questionnaire. The graph shows the 6 UQ scales in which the mixed reality training performed best, followed by the virtual reality training. The average scores of the scale results had the same result. With the raw NASA TLX, we assessed the participants' perceived cognitive workload. As can be seen, the overall score indicates that the VR training perceived the best average RTLX score, followed by the mixed reality training. A statistical analysis indicated no significant difference between the groups. Participants rated their interest in the respective training method by the question, "The exercise topic was conveyed in an interesting way." A post-hoc test showed that participants were significantly more interested in mixed reality training than in real training. The subjective training success was perceived by the question, "I feel able to transfer what I have learned without any problems." Thereby, the mixed reality training achieved the best result. 1 week after the training, participants answered an online test with 10 questions to assess the training success. The response rate for the test reached about 90%. Participants in the VR training and MR training answered significantly more questions correctly than participants of the real training condition. Regarding our research questions, the results of the UQ scale attractiveness, the RTLX workload, the subjective training success, and the test results indicate that the training success in VR and MR is higher than the conventional method. The slightly better subjective ratings and test results demonstrate that mixed reality training is more suitable than virtual reality training. The results of the training duration, the training interest, and the UQ novelty scale indicate that the virtual methods increase the motivation to engage with a training topic. The presented study has some limitations. The between subjects design implies that variations due to the subject's motivation or abilities could exist. Some of the collected results were obtained by self-reported measures, whereby the possibility exists that participants exaggerated their rating or were too embarrassed. Also, the avatar's abstract and transparent representation in the virtual reality training condition might have influenced the training success. Finally, the results demonstrate that both collaborative virtual training methods provide the potential for better training outcomes than conventional training methods. Considering that these technologies offer more possibilities than those implemented in this training, they can help to improve the training of civilian explosive ordnance disposal personnel and therefore increase their safety. In addition, it should be noted that this training has dealt with the functionality, designations and implications of a single scenario. Nevertheless, these results can also be applied to other collaborative application areas. Thank you for your attention. If you have any questions, please feel free to contact me.